Good afternoon, everybody. My name is Ranjay Krishna, and I'm here to talk about our paper on visual relationship detection. Now, if we take these two images that both contain a llama and a person and ask today's state-of-the-art detectors to tell us what's in them, they will identify the llama and the person, but they won't be able to distinguish between the two images. While objects are the core building blocks of an image, it is often the relationships between these images, between these objects, that help define the story of a scene. It helps us distinguish when a llama is simply standing next to a person versus when a llama is chasing a person down. If we take a look at the visual world around us, like this scene very close to us, we can see that objects are constantly interacting with each other in numerous different ways. For example, at a quick glance, we see that a woman on the left, or on the right over there, is holding her cell phone. A woman on the left is carrying her backpack, and two people in the middle are interacting with the sign. While one person is climbing the sign, the second one is comfortably sitting on it. So in this paper, we want to be able to understand all of these relationships. More precisely, the input to our system is an image, and the output is a series of relationship triples. Now let's break this output down. First, we want to identify both the people in this given image. We also want to identify the two horses and localize them. Next, we want to associate each person with their respective horses with the correct relationship. In this case, both the people are riding the horse. And finally, we also want to be able to say that the horse on the left is in front of the horse on the right. Now, relationships are not a new concept. They've been studied extensively in the context of both spatial relationships as well as the actions that humans perform. In fact, there's also been a lot of work in understanding common relationships, like people wearing shirts, and they've shown that relationships can both help object detection as well as image retrieval. Now, unlike all of this prior work, we provide a uniform framework that not only understands spatial relationships, but also actions. And not only do we understand the common relationships, we can predict the rare and unseen ones as well. Now, we've already seen how diverse a single scene can be. So to truly capture the visual world, we resort to using the visual genome dataset, which contains a large number of object and relationship categories. Now, when using such a large dataset, we make two very key observations. The first observation is that the quadratic explosion that occurs in the number of detectors we need. For example, let's say we just want to detect relationships between a person and a bicycle. On the right side, we have all the different ways a person can be interacting with this bicycle. A person can ride a bicycle, they can fall off of one, they can carry one around, or even throw one. So if we wanted to detect every single one of these relationship triples, we would need an unscalable number of detectors. More precisely, given n objects and k relationships, this would lead to an n squared times k number of detectors. The second key observation is that relationships often occur in a long-tail distribution. Some relationships, like cars on the street and dogs riding skateboards, are very frequent in the dataset. And other relationships, like elephants drinking milk and a cute dog riding a surfboard, they tend to be very rare. Now, this makes it very difficult to do supervised training because our models tend to prefer the common ones over the rare ones. So with these two observations in mind, we design our model to include two modules: the visual module, which will tackle the problem of quadratic explosion, and the language module that will tackle the problem of long-tail distribution. Now let's dive into this model. First, our input, again, like I mentioned, is just an image. We will first use selective search to generate a list of object proposals. Next, we'll sample two of these boxes, let's call them B1 and B2, and we'll send them through an object detector. Now this object detector will output a score of how likely each box is going to be classified as a particular object. Next, we'll take the union of the two boxes that we sampled and pass that through a relationship detector. This relationship detector's job is to predict the correct relationship between the two objects in the scene. In this case, we would want it to predict the relationship ride. Finally, The output of our visual module is a probability score of how likely a particular relationship triple is given the two bounding boxes. Here we define the triple T as the two objects O1 and O2 and the relationship R between them. Now, if we take the triple that scores the highest from our visual module, we see that it detects both the person and the horse correctly, but it incorrectly labels the relationship. It thinks that the person is in the horse, something I've never seen before. So now, to actually aid the visual module, we introduce the language module. The language module takes the individual word embeddings of a particular relationship triple. In this case, for example, we might take man, ride, horse, and its output is a score of how likely that triple is to occur based on just the language embeddings. Now together, the two outputs from the modules help us get the probability score of how likely a triple is to occur given not just the bounding boxes, but also the language priors. Now, it's important to note here that we make the assumption that the selective search outputs are independent of the word embeddings that are learned. And now, as you can see, our model together with the two modules can output not only the correct objects, but also correctly outputs the correct relationship, ride or riding. Now, because our visual module detects both objects and relationships individually, we tackle the problem of the quadratic explosion and only require n plus k detectors. Similarly, the language module helps us tune rare relationships and make sure that our model doesn't always predict the very common relationships. For example, earlier we saw that in is a very common relationship, which would get predicted. But because a man is never in a horse, our language module learns to score that lower than the relationship triple of a man riding a horse. This helps the visual module fine-tune its scores to predict the correct output. Now that we know how our model works, let's take a look at how we perform training. So we initialize both our object detector and the relationship detector using pre-trained ImageNet features. Next, we train our object detector using a procedure introduced by RCNN in 2014. Similarly, we use the union of the two boxes to train our relationship detector. And finally, we fine-tune both the object detector and the relationship detector using a ranking loss. This ranking loss aims to rank correct relationships higher than the incorrect ones. Now recall that some relationship triples are very common, like dogs riding skateboards, and some are very rare, like dogs riding surfboards. But these two relationships should be equally likely because both a skateboard and a surfboard affords the relationship ride. So to train the language module, we define a function d that measures the distance between two relationship triples. Now this distance is measured as the sum of the cosine distances of the individual components of a relationship triple. In this case, the distance between these two triples is the cosine distance between a skateboard and a surfboard. And then we perform knowledge transfer by ensuring that the difference between the likelihood of predicting these two triples is proportional to their distance in semantic word embedding space. And finally, we train both these modules iteratively, holding one module's parameters constant while training the other one, and vice versa. Now that we have our model trained, let's take a look at some of our results. So given this example input image, our model learns to predict spatial relationships. It predicts that the little girl is to the left of the lady. It also learns to compare objects. It thinks that the lady is taller than the little girl. Now, it's important to note here that our model has learned that relationships are directional. By switching the order in which we sample our boxes, it predicts two completely different relationships. Our model also learns verbs. In this example, person wearing a shirt and person wearing skis. And finally, it also learns prepositions. For example, the person on snow. So together, all of these outputs help tell a more complete story than just detecting the individual objects in the image. Next, we do an ablation study to figure out how the different components of our model help our output. And we compare it against a baseline implementation of relationship detection from 2011. This baseline implementation suffers from not being able to deal with the quadratic explosion of detectors and always tends to detect the most common relationships, in this case, a person wearing a shirt. It's unable to detect the horse. Now, our visual module overcomes this problem and is able to detect all the objects, but it, like I mentioned, doesn't always detect the right relationships because of the long-tail distribution. Now, finally, our language module comes to the rescue, and we see a significant boost because our model can not only detect the common ones, but also the rare relationships. However, our model is not perfect. For example, here, it thinks that the male police officer is riding the female police officer's bike. Another example of where it fails is here, where it thinks that two people are throwing the same frisbee. Now, it doesn't have any higher level rationale that determines that if one person is throwing a frisbee, a second person cannot possibly be throwing the same frisbee. And the last thing I want to leave you with is that because our modules, both the visual and the language, learns relationships and objects individually, it can combine those objects and relationships to predict novel relationship triples that it's never seen before. For example, it's seen over 900 examples of a person sitting on a chair and around 29 examples of fire hydrants on the ground. And now, not only can it detect a person sitting on a chair, but it can also detect when a person is sitting on a fire hydrant. Additionally, it's seen a lot of examples of people riding horses, and it's seen a lot more examples of people wearing hats. So now, it can detect when a horse is wearing a hat, something it's never seen before. I urge you all to come to our poster. We can dive into the math, look at some more results. Thank you so much.